So we're interested in ice because it means water, and while subsurface ice may or may not be important for indigenous Martian life, it's clearly not as nice as subsurface liquid water. Subsurface ice is likely to be an important resource for us when we colonize Mars. Okay. So the two missions we're going to talk about and talk about how they relate to one another. Mars Odyssey, as we've talked about, really had a primary mission, and it has recently been taking on that secondary mission of communications relay. 3 main instrument packages on the orbiter. Themis here is an infrared camera. So Mars Odyssey went into orbit 2 launch windows after Mars Global Surveyor went into orbit. So Mars Global Surveyor had been in orbit for like 4 years, taking what at the time was fairly high resolution images of the surface, as well as having the laser altimeter, the Mars Orbital Laser Altimeter. So we were already getting much higher quality visual images from orbit than we had with the Mariner and Viking missions from Mars Global Surveyor. The infrared camera is obviously taking data in a different wavelength. Okay? A lot of our advance in science has been tied to the development of instrumentation that allows us to make different kinds of observations than we can necessarily make with just our raw senses. Okay? So we can't see in the infrared, but if we have a camera that can capture infrared images, that gives us a different set of data about the Mars surface than if we took visible light images. So in particular, if you take daytime and nighttime infrared images, you can see how rapidly a given area of Mars heats up and cools down. And that tells you something about the structural composition of that area. Solid rock tends to heat up and cool down more slowly because you've got this huge thermal mass. So when daylight comes, it takes a long time for that mass to heat up, and similarly it cools off more slowly at night. If you have an area that is where the surface is more sandy, you've got individual sand grains which by themselves heat up and cool down more slowly. So by looking at these infrared images, daytime versus nighttime, we can get some overall ideas of the composition. The infrared camera also provides a different it's just a different data set. The Marie instrument is the one that was mentioned that was monitoring radiation levels. So that was really just to see how difficult it would be for humans to go to Mars. They basically found about twice the level of radiation that they were necessarily expecting. So it's going to be a little bit more of a hassle dealing with radiation than maybe we thought earlier, but probably not insurmountable. What we'll be talking about today, though, is the Gamma Ray Spectrometer suite of instruments. There's actually 3 instruments here. And these are collecting data. Well, the gamma rays is a whole different part of the electromagnetic spectrum. We'll look at it in a minute. They're also associated with this package are 2 neutron detectors. So if we look here, blow this up a little bit, the gamma ray detector itself is on the end of this boom. that's separating it a little bit from the spacecraft. And that's important because the spacecraft itself, as it's bombarded with cosmic rays, gives off a low level of gamma radiation. And so you want to separate this gamma ray sensor from the rest of the spacecraft. And then there's the high energy neutron detector, which is right here. And there is the low energy or regular neutron spectrometer, which is also here on the spacecraft. So this is doing remote sensing of Mars. So it's going to be looking for neutrons and gamma rays that are coming off of the surface of Mars. Okay, questions? That's all plain as day.
What's the point of star cameras?
The star cameras are navigation aids. Not so critical for when it's in orbit, but as the probes are going from Earth to Mars, in the past at least, and currently, spacecraft will, there's no solar system-wide GPS. There's no solar system-wide global positioning system that we have in place yet. So there's a couple of ways how you can tell where your spacecraft are as they're going from one planet to the other. You can just try to do a inertial tracking. So we knew we fired the rockets and sent it off in this direction, and we've done X thruster fires in the meantime, and so we expect it to be here. That's not always completely reliable. So the spacecraft have these star cameras that allow them to take pictures of specific bright stars, a whole suite of them, as well as keeping track of where the sun is, as a way to kind of triangulate where they are in the solar system and are they on the right path to Mars that they're supposed to be on. Going forward, we might use pulsars as a galactic GPS, but that's not really in play yet. You got the antennas, you got the solar arrays, and so forth. So this is a pretty basic, pretty standard kind of orbiter. Again, it is doing more global reconnaissance. That's the advantage of orbiter missions, that you can collect data from the whole planet. Our Odyssey would have been sent on a Hohmann transfer pathway to Mars, as we've talked about, that Keplerian kind of orbit, and would have been captured into a Mars orbit with a combination of thruster burn on the one hand to slow it down, and also going through the atmosphere to also slow it down. Slow it down enough that it's into this elongated elliptical orbit around Mars, and then with subsequent passes through the atmosphere to slow down and shape the orbit, it eventually gets into a mapping orbit where it's circling Mars. Odyssey, like most orbital missions these days, is in a polar orbit. It's basically going over the North Pole and South Pole, so that as Mars rotates underneath, the orbiter has the ability to look down at essentially every spot on the planet as it goes around one orbit to the next. Okay. So what's it actually measuring with the Gamma Ray Spectrometer suite of instruments? Mars, like other objects, is emitting various kinds of radiation off into space. And that's what is what's being shown here. As you have cosmic rays coming in, cosmic rays are these high energy particles that are coming from throughout the galaxy. They're alpha particles and protons and other small nuclei accelerated to very high velocities by galactic processes. Because Mars has less atmosphere, some of the cosmic rays are going to be filtered out by the atmosphere. That's clearly what's happening here on the Earth, but Mars has a thinner atmosphere, so a lot of these cosmic rays get down to the surface and smack into atoms in the minerals and rocks and so forth in the surface of the planet. And those high energy collisions are going to generate a bunch of debris essentially. The high energy collisions can knock neutrons out of atoms. So a lot of what's happening here is, some neutrons just get ejected very fast from the soil, and they're basically go up through the atmosphere and out into space. That's one of the things that the high energy neutron detector is detecting, those neutrons that are coming straight out. A lot of other neutrons, they're going to be knocked off in all different directions. Some of them are going to bounce around in the crust, and as they bounce around and interact with other atoms in the crust, each interaction is going to sap some energy, slow them down a bit, and so you have basically fast neutrons coming out and slow neutrons, what are called thermal and epithermal neutrons. But essentially you've got high energy neutrons and lower energy neutrons. So that's why you've got 2 neutron detectors on the spacecraft. And you've got a gamma ray detector because there's also gamma rays going to be coming off of the surface of the planet. As these neutrons and other debris continue to collide, some of those collisions result in the atoms adopting a higher energy state. And in order to get back down to a lower energy state, they give off gamma rays, just like a very hot bar of iron would give off infrared and visible light as it's radiating energy off. So there are gamma rays coming off from different sources. Some of these collisions, there are naturally radioactive materials in the surface of Mars, and some of them decay by giving off gamma rays, and so those are going to be coming off as well. But what's especially important for the ice story is that hydrogen atoms in particular in the crust can capture a neutron, and when they do, they give off gamma rays at a particular frequency. So, again, the probe is up in orbit. There's no way for it to directly interact with what it's trying to look for on the surface. And so with remote sensing, we basically have to say, well, what is coming off of the surface that can be detected from orbit, and how can we then interpret what we're detecting from orbit in order to work backwards to know what kind of stuff was down on the surface where we're not actually taking direct samples. Okay, this gamma ray spectrometer can look for lots of things besides just water ice, or we'll talk about what it's seeing. Every kind of element is going to have a different gamma ray profile in response to being bombarded by cosmic radiation. So, this is not necessarily germane for the story today, but just to show you that this instrument suite can do things like map the percentage of iron that's found in crust on different parts of the planet. So, I mean, the data that is being returned is essentially a global map fine-tuned to whatever is being measured by the different frequencies of gamma rays and neutrons and so forth that you're looking at. So one of the early results out of the Odyssey mission is this article and related articles that was looking for the distribution of hydrogen in the near surface of Mars. Okay? Hydrogen is an element just like iron, just like nickel, other elements. Why would we be interested in the distribution of hydrogen in the crust of Mars? Jalen? H2O, okay. Most of the hydrogen that is going to be present in the crust and interacting with these cosmic rays and the neutrons that are being kicked out is likely going to be bound up in water, hydrated materials. And a large proportion of that, theoretically, could be water and water ice. Okay. So I just wanted to show you a couple of figures from this paper. This just shows you the kind of readings that you get out of the gamma detector, part of the gamma ray spectrometer. I just want to show that, as we talked about, hydrogen, when it captures a neutron, gives off a very characteristic peak of gamma radiation. And so the instrument up in orbit can be fine-tuned to look at how much gamma radiation is coming off at this particular energy level, and that will be a measure of how much hydrogen is in the, I don't want to say soil because it's not really soil, how much hydrogen is in the regolith surface on Mars underneath the spacecraft that is capturing those neutrons that have been given off and then radiating off the gamma radiation. So you look for this, and you see how much of peak you have here, and clearly the higher the peak here, the more hydrogen there would be expected to be in the surface of Mars directly under the spacecraft where you're collecting that information from. So as the spacecraft goes around in orbit, you can just say, how much hydrogen signal am I getting? How much hydrogen signal am I getting? Like every 20 seconds it says, how much hydrogen signal am I getting? It'll move on in its orbit, take another measurement, and you can basically use that to build up a map of where you find a lot of hydrogen in the surface and where you find less hydrogen in the surface. Is that clear? I mean, basically, you have to take what the surface will give you, and then you've got to be able to interpret it. So one thing they did was just to, average these data by latitude. All the observations that they take when they went over the equator, different parts of the equator, but all the equatorial readings, all of the readings at 10 degrees north, 20 degrees north, 30 degrees north, 10 degrees south, 20 degrees south, and so forth. And you get this kind of image. Basically, there are the results from the 3 different instruments that make up this suite being plotted as a function of latitude. Okay. So, how do you interpret this graph? What's on the x-axis? Okay. So the x-axis is the horizontal. What's minus 90 represent? No, latitude is not elevation. What does latitude measure?
The width of the Earth or any planet, I guess.
Yeah, not the width. What does 0 degrees latitude represent? On the Earth, on Mars? Okay, 0 degrees is the equator. Okay. So minus 90, one of the poles. South pole, okay. Plus 90, North pole, okay. So we essentially have a latitudinal gradation here going from the South pole through the equator to the North pole. Now, let's just look at the hydrogen gamma radiation signature, which is this line here. Let me do it in red. Again, what does this measurement indicate? High levels of hydrogen-related gamma radiation means what about the level of hydrogen in the surface underneath the probe at that point?
Can you repeat that?
High levels of hydrogen-related gamma radiation indicate what about the abundance of hydrogen? There's a lot of it. Okay. So where do you see on this graph the highest amount of hydrogen in the surface? At the South Pole. Okay, so we got a lot of, we have from the hydrogen-related gamma radiation that's being detected by the spacecraft, that's indicating that the surface at the South Pole has a relatively high abundance of hydrogen. And then as you go toward the equator, it drops. So we have lower levels of hydrogen. And then as you start going away from the equator in the northern hemisphere, what happens to the amount of hydrogen?
It rises.
It rises again. Why isn't it not symmetrical with the South Pole? That's the question to think about. Okay, if we look at the epithermal neutrons, which is this curve here, we see that when the hydrogen-related gamma radiation is high, what do we know? What do we see about the amount of low-energy neutrons coming off? It's lower. Okay. So the way we would interpret this is that the surface toward the South Pole has a lot of hydrogen in it that is soaking up those low energy neutrons, capturing them, which is why we see fewer of them. And then that neutron capture causes the gamma radiation to be released. Okay. So we would expect to see this negative relationship between the two. Okay. So, if there's a lot of hydrogen in the surface at the South Pole, what might that indicate? What are we looking for? Water, ice. Okay. So that makes sense. There's in the regolith at the South Pole, it looks like there's a lot of water, and that water is in the form of ice. Why would we see less water as we move in the surface as we move toward the equator? Soil's going to be, well, why would it be dry? The heat's going to do what to water ice? Melt it. There's a very little atmospheric pressure on Mars, so if the surface water goes from ice to liquid, it's going to evaporate off the surface. Okay, so this all is beginning to make sense. The surface layers, at least at the equator, are expected to be drier.
Why does it, like, do you actually know why it doesn't?
Yeah, so why don't we see that at the North Pole? Wouldn't we expect to see water ice in the surface layers at the North Pole? So it would kind of mirror what's going on in the South Pole. Well, at the time these data were taken, the North Polar region is covered over by frozen carbon dioxide. The polar cap basically covers this. And so there's no way to get a hydrogen signal through that because the polar cap is all, frozen carbon dioxide. Presumably there's water in the surface layers, but that's covered over. And this technique basically can only penetrate about 80 centimeters down through the surface. So if you've got a kilometer or two of frozen carbon dioxide dry ice on the top of the polar region, you're not going to see the water ice that is buried underneath that. Okay. So you get this kind of a map. This map is actually not showing the hydrogen-related gamma radiation, but it's showing these low-energy neutrons. And in the areas that are dry, in the area where there's not any water ice in the surface to capture those low-energy neutrons, we're going to tend to see a lot of them. So, basically more neutrons means drier surface areas on Mars. And as you might expect, the pretty much anything south of 60 degrees south latitude is, I don't want to say saturated because that has a particular meaning, but has a lot of projected water ice in it. This white line here is the theoretically predicted area where ice would be stable within this distance of the surface. Anywhere closer to the equator, then the surface would be too warm for water ice to be stable, and you'd expect those surface areas to be baked of their water. So this is a pretty flashy result when it came out shortly after Mars Odyssey arrived. Because it indicates that if you go to high latitudes and dig down into the soil, you're likely to find a lot of water ice. At least that's the interpretation based on the measurements from orbit. And we're talking about a lot of water ice, anywhere from 15 to 40% by weight water ice. So essentially, you dig up a bucket of this surface regolith, bring it into your heated habitat, and you can, harvest half a bucket of water. Not bad. Here's just a cleaner picture based on at least a Martian year worth of these observations. You can see that it's the North Polar regions as well as the South Polar regions. If you've got the time to make the measurements when the North Polar cap is not in place, you see the same abundance of subsurface hydrogen, which we interpret as water ice. Now there are some interesting regions at low latitudes that also show a hydrogen signature, like this would be, okay, here's the Tharsis Montes, here's Valles Marineris, Elysium is over here, so this would be, that area in between. Clearly there's an elevated signature of hydrogen coming from this area. So what's going on there? It's really not necessarily clear yet. Okay. So that brings us to how this relates to the Phoenix lander. That's remote sensing from orbit, and it's a nice story, but did anyone or did the Odyssey rover touch any water ice? No. It is interpreting the radiation and neutron signature that's coming up from the planet, the thing that can be detected from orbit. And a very important concept with remote sensing is the idea of doing ground truthing. So the orbiter is giving us global coverage of the planet, measuring certain aspects of the planet, and we're using that to interpret this global map of water abundance. But you really want to complement that with someone going to a location, actually taking measurements in place, and relating those measurements to the remote sensing measurements from orbit so that you can validate or have more confidence in your remote sensing data. So the Phoenix lander mission was designed from the start with the Odyssey results in mind, with specifically the idea to validate that interpretation of the hydrogen signature, that it really does mean that there is water ice down there. So the Phoenix lander, clearly it's a lander, it's not even a rover. It's not going to be able to do a global sample of anything. It's going to be sent to one place. And that one place is about, it's not quite at the North Pole. It was like at 60 or 70 degrees north, as I recall, something like that. And has a scoop, so it can scoop up samples and analyze them. Clearly, if we are interpreting that the soils, the regolith at high latitudes have high proportions of water ice, we would expect to be able to sample that regolith, take it into various instruments to analyze it, and see whether there's ice there or not. The lander had a couple of main instruments. One of them is this TIGA unit, the Thermal and Evolved Gas Analyzer. It's essentially 8 high-temperature ovens. Each of them could be used once. And so the idea is you take a sample of the soil. I'm just going to start using soil, even though it's not the proper term. You take a sample of the soil, you drop it into one of the ovens. You open up the doors on that oven, you drop the soil sample in, you close the doors, you heat up the sample and progressively heat it hotter and hotter and hotter. And then that drives off materials that then can go into a mass spectrometer that allows them to identify water or carbonates or other kinds of materials that emit gases when they're heated up. I mean, water ice, clearly, if you heat it up, it's going to become water vapor. That goes into the mass spectrometer. You see a big spike at a mass of 18, which is 1 atomic weight for hydrogen, another atomic weight for hydrogen, and 16 for oxygen. Boom, you see a lot of water. But there are other things that can be vaporized when you heat them up hot enough as well. So that's what's going on with this instrument. And again, you're going 300 million miles to Mars. You've got an instrument that has 8 ovens, and once an oven is used, can't be used again. So you want to make them count. Similarly, there's the Mika unit, microscopy, electrochemistry, and conductivity analyzer. Just think of it as a wet chemistry lab. So in this case, you can take a soil sample, add water to it that you bring from the earth, so it's deionized water, and you can see are any salts dissolved into this water. Does the the resulting solution conduct electricity because there are salts. You can do various kinds of chemical analyses to complement the mass spectroscopy you get from the TIGA instrument. So we have basically the ability for this arm to reach out and to sample various locations within reach. Okay. So, it's not a rover, it's a lander, so it's kind of constrained in terms of its mobility. So you can sample different areas, and you can dig down as deep as you can go until you hit something that you can't scoop out with the scoop. I won't go into a lot of figures of the results from the TIGA and Mika instruments, but basically the Phoenix mission did find ice in the soil. We'll talk about that in a little bit more detail with just some images. So there's a shallow ice table. You dig down a few centimeters and you hit ice. And not only that, you can measure the alkalinity of the soil. It's much more alkaline than the soil, for example, at the Meridiani Planum site. You can see it contains calcium carbonates, other kinds of minerals and salts. In particular, I want to just mention one of the big findings out of the Phoenix mission was finding a chemical called perchlorate. And we'll come back to that when we talk about the Viking biology results. But, basically, the mission operated until the North Polar season shut down the mission. By the end of the season, the lander would have been covered by many, many feet of frozen carbon dioxide. It's clearly not going to operate much after that. But they did find water, ice. They found particular soil chemistry that would be perfectly fine for growing earth plants in, if you had a greenhouse with this soil and water and so forth. It's a little bit alkaline, so they say, well, it's not so good for strawberries, but you can grow your asparagus because asparagus likes more alkaline soils. Strawberries like more acidic soils. Not the most serious comment on the research, but something that came across in the news stories. But it's pretty obvious just looking at the results from some of the scoops. So here is just a photographic examination of what was uncovered in some of the scoops. There are two kinds of ice detected in the soil. There are these light-toned patches that is relatively pure ice. Deposits of relatively pure ice buried in the soil. And these other images here are also showing soil profiles that have ice in them, but in this case, it's not the same concentration of water ice. It's more, if you look at the structure and the chemistry of the soil itself, that there is water ice throughout between the different particles of soil. So it's not really obvious here, but you've got this ice-laden soil, and then you've got these actual light-toned deposits of relatively pure ice.
So did the lander just spin around in a circle and take dirt, or did it?
The lander came down on 3 legs, 4 legs, landing pods. Comes down on retro rockets. The pods hit, and the scoop is pointed out one direction. So it can't even spin around and take soil from over here. You can basically, there's a front and a back for the lander. There's a front of operations where you can reach out with this scoop, take a different soil sample, and bring it back to one of the ovens if you're putting it into the TIGA unit, or to dump it into one of the chemistry wet labs if you're doing it in the Mika unit. There's some amount of, it's not just scooping from the same place all the time. There's some range, but it's like this much of an angle in front of the spacecraft.
So why do they pair it with like 8 different? I mean, if it's not even going very far, why did they need 8 samples from the same?
Well, you want to analyze the soil sample from the surface and then from lower depths, so you can do a profile. And as we'll see, there is variation, spatial variation, even within the range that the arm can reach. So, ideally, the investigators probably would have wanted to send 16 or 20 of these ovens so that they could do more samples, especially since they had a lot of difficulty actually processing the soil. They expected to be able to reach out, grab some soil, and then just dump it through the screen into these ovens. But that worked very fine for dry desert soil from Arizona, where they were testing the scoop. But the soil at the Phoenix site had this problem of clumping, probably because of the frozen ice and so forth in the soil. So the first time they took a sample and tried to dump it into the oven for processing, they couldn't actually get it down through the screen that's on the oven to keep the rocks out, because the soil itself kind of clumped together. So they had to figure out how to sample soil in order to collect it as a fine enough sample so it would get down into the ovens. So they didn't exactly waste one of the ovens, but clearly by the time they figured that out, the sample that they ended up processing on that first oven was not as interesting as it could have been.
Wasn't it that like the first thing that they put in the oven was like too clumpy or something to go through?
Yep, that's exactly. So, best laid plans, until you get to Mars, until you get to a specific location and you see what the problems are that you have to deal with, can't necessarily anticipate them all. So, this is just showing some of that variation. The triangles are where they found relatively pure ice, this light-toned ice deposit. So you can see it's kind of, here's a concentration of that relatively pure ice, whereas these are places where they found ice bound up in the soil. So there is our icy soil as opposed to that light-toned, more pure ice.
You have a question?
Yeah.
When you say ice, do you mean like water ice or like?
Yeah.
Oh.
Yeah, so, that's why you bring it into the mass spectrometer, into the TIGA ovens, and into the Mika unit, so you can actually tell that, yes, it is water ice. It's not carbon dioxide ice that's in the soil. We can skip. Here's just another indication. It's not real obvious, but you can maybe see that between Sol 20 of the mission and Sol 24, at this point, they just scooped out this trench to take a sample and found some of this light-toned ice deposit. And you can sort of see that over the span of 4 days, some of that is disappearing, as you would expect if water ice were exposed to the atmosphere of Mars. If this were carbon dioxide ice, it would probably have disappeared within a sol or two. So that's just a kind of a qualitative indication that it's water ice we're dealing with. But then you bring the samples into the ovens, into the instruments, do the actual analysis. You can say, yes, we find water ice, we find carbonates that look like they've been deposited in the presence of water. We see these other minerals and so forth. And the overall result of this is that the Phoenix results basically do ground truth the story that we're developing from the data collected from orbit by the Odyssey mission. Just one last little item here. Clearly, if you're coming down on retro rockets, you're going to disturb the soil on the way down, right? And one of the first things they noticed was directly underneath. So here's one of these landing pads, and this is looking underneath the spacecraft, under the lander, from the camera that's on the arm. You can see that the retro rockets coming down exposed these very bright, shiny masses. And over time, this mass here, I forget what cute little name they gave it, basically over time evaporated away. And so just, coming down on retro rockets was a pretty good scoop for removing the surface layers of soil and exposing the ice underneath. So yes, once again, we've discovered water on Mars. Like every 3 or 4 years, we discover water on Mars, but it's in a different format. Here we're talking about, yes, we've actually, this is the first mission that has actually touched and analyzed water on the surface of Mars. Actual water. In the form of this water ice. Bertram, is that a stretch or a...
Really quick, like, you said that if it was dry ice, it would evaporate it.
More quickly, yeah.
So why is the pole covered with dry ice that hasn't evaporated?
The dry ice at the poles are seasonal. So during the winter on the North Pole, you'll get carbon dioxide freezing off onto the pole. During the northern summer, it'll evaporate away. Same thing on the South Pole. There is some differences between the North and South Pole that we should probably talk about. See if I can work it in next time. Okay. Have a good weekend, everyone.